Hi everyone, in this video we're going to discuss on 7.3, which is thin lenses. There are two types of thin lenses, which is a convex and also a concave lens. So convex lens is normally thick in the middle. So if you look at this one, we have very thick middle and very thin sides. Okay, but for concave lens, we have very thick sides, okay, and very thin middle. Next, we're going to see the name of these lenses. For convex lenses, we have three types. We have double convex, means that both sides are convex. Plano convex means that one side is convex, the other side is plane, straight, plane. And convex meniscus means that one side is convex while the other side is concave. Next, we have concave. So we have three types of names for these types of lens, which is double concave means both sides are concave. Plano concave means that one side concave, the other side is plane. And concave meniscus means that one side is convex while the other side is concave. Now this is really important. The reason why is that it's normally for questions that don't give us picture of the lens. So when they normally give us the name of the lens without giving us the picture, it is really important for us to know this so that we can imagine what type of lens that we need to sketch. Now let's take a look at the terms used in thin lenses. For convex lens like this, we have R1 for this side, R1, and the center is C1. And for this side is the R2 and the center is C2. It's basically the overlapping of the two spheres. Basically, you overlap and you can get a biconvex lens. But for a concave lens, it's normally just the sides of two spheres, and we connect it with these straight surfaces. So like this one is the R2 for this yellow circle of C2, and this one is the R1 of the radius C1, like that. Next, we have ray diagrams. We are not going to go too deep into the ray diagrams. It's just we want to see the location of the object. If it is more than double of the focal length, it is red. Okay, and the object is real. Why is it real? Because the image formed is on the other side from the object. Okay, this one also the same. It is real image because it is formed on the other side of the object. This is for the object when it is placed at double the focal length. Next, we have when the object is located between double focal length and the focal length. The image is again real, but this time it is magnified. Again, the meaning of real image is when the image is formed on the other side of the object. Okay, for the object that is formed on the focal length, we will normally don't get any sharp image. And then if the object is placed less than the focal length, the image is normally virtual. How do we know that it is a virtual image? Because it is placed on the same side as the object. So that's how you know that this is a virtual image. And for a distant object, now this one we have done in our experiment 5, if I'm not mistaken. We tried to get a distant object. Remember the trees from the outside of the lab so that we can determine the focal length of the lens. So this is it. If the object is very far, so we're going to call it as infinity, then the image formed is on the focal length. So real, inverted, and diminished, where the image distance is the same as the focal length. This one, we have done this in our experiment 5. The good thing about concave lenses is that the image form is only one type, which is virtual, upright, and diminished. It is formed on the same side as the object, and it is always smaller than the object. This one is the summary of all the locations of concave lens and convex lens. We have red, rays, rim, real, virtual, zoom, and also red. For concave lens, we have wood. Alright, this is the important part for the focal length of lenses. It is not the same as mirror. So for mirror, we have f equals to r over 2. You cannot use this equation anymore when it comes to lenses. One of the ways that you can determine the focal length of the lenses is when you are given the refractive index of the lens itself. So refractive index of the lens divided by the medium where the lens is located. For if the lens is located in the air, then and medium is 1.0. If it is located in the, let's say, oil, maybe it becomes 1.35. I don't remember the refractive index of the oil. Let's just say this. So like this, and you minus everything lah. And then you can see here 1 over R1 minus 1 over R2. Now this part we have to determine just like we have determined using the spherical surface equation. So how to do it? How to determine which one is R1 and which one is R2 and the symbol whether it is positive or negative. Now let's go to the next slide. Alright, now in this slide, they can help us to determine whether the R1 is positive negative or the R2 positive negative. It depends. Okay, let's take a look at the first one. If we are given a biconvex, so the light rays normally comes from one side lah. So it will hit on the first side like this. Okay, the first surface like this. It hits here, and you have to remember you can use the Suker-Bonchet principle. Okay, the Suker-Bonchet. We can see that in the R1 it is positive because it is on the Bonchet side. But if you continue, if the light ray is continued, goes to the second, hitting on the second surface, you can see that this one is already close. So the R2 becomes negative. Okay, let's proceed to the next shade. For a plano-convex, again, if the light ray is hitting on the first surface here, we can see that this is a Bonchet. So R1 becomes positive. But as it proceeds to the second surface, this one is plane. So it is infinity. Okay. Next, we have a convex meniscus. Again, we're gonna hit our light rays, gonna hit the first surface. This is a Bonchet, hence it is positive for the R1. Proceed with the second surface. Again, this is also a Bonchet, hence the R2 is positive. Now we want to determine for the R's for the concave lenses. So again, the first light ray hits the first surface. This is a concave, kurus, so negative. Hitting on the second surface, gemuk, so it is positive. Next, we have a plano-concave, hitting on the first surface, kurus, hence negative. Hitting on the second surface, it is a flat, hence it is infinity. So for concave meniscus, the first surface is Bonchet, positive. The second surface is also Bonchet, hence R2 also positive. Now let's do a few questions so that we get to know more about thin lenses. So we have here 10 centimeters tall object is placed 20 centimeters from a diverging lens. Ooh, look at this word, diverging lens. What is this? Now this is actually a concave lens. So concave lens always have negative focal length. Okay, so let's see, I have 10 centimeters. What is that? I think this is a H of the object. And then I also have 20 centimeters. It seems that this object is placed 20 centimeters from a diverging lens, means that this is a U. And then it is 5 centimeters tall, which is the image lah. The virtual image is 5 centimeters tall, so HI equals to 5 centimeters. So it says here that it is a virtual image, so normally virtual comes with upright. And because of that, HI is always positive because it is upright. Virtual is upright. Now back to the questions asking for the focal length of the lens, and also they ask us to sketch the ray diagram. Alright? Because we have HO, U, and HI, I'm going to use magnifications equations. So we are going to combine the HI over HO equals to negative V over U. We're going to substitute 5 over 10 equals to negative V over 20 so that we can get the V equals to negative 10 centimeters. So obviously this is a virtual and upright. Now this matches with our summary of lenses ray diagram. You can see here for concave lens, we always have VUD, V-U-D. So when we go back to our calculation, we can see obviously it is verified that our V is negative 10 centimeters, which gives us that this is V and U already. Okay? And then from here, we're going to use the thin lens equation. That's 1 over V, 1 over F equals to 1 over 20 plus 1 over negative 10. So our focal length is going to end up with negative 20 centimeters, which fits the characteristics of a concave lens, which is negative focal length. The next part is we are going to sketch the ray diagram. So what I'm doing here, I'm drawing a principal axis, and I'm about to draw the principal lens, basically. So you just follow me. Now this line is a line that I will erase later. I just use it to guide me to where the light ray is gonna bend. Okay, so because our focal length is negative 20 centimeters over here, so I'm gonna put here negative 20. So this is our focal length. So I'm assuming that our focal length is the same for this side. So even though you are doing the sketching, just make sure they're pretty much the same length, you know. So this is another F. So look at the object. The object is on the same location as our focal length. So what I'm going to do is I'm going to put my object just here. Okay, this is my object, and do not forget to label over here. Okay, and next what we're going to do is we are going to draw sketch the ray diagram. First, go straight up to the principal line, and then I'm going to reverse to this side. Okay, pretty much this way. It doesn't want to move much. Okay, but this one I'm gonna make it a serrated line like that, but I'm gonna continue extrapolate the line, make sure it is pretty much in line, and my arrow is important. There you go. That is one line. We need to find another line so that they can intercept with one another. So once it is intercept, we know that is where our image should be formed. Okay, the next one, I'm gonna go from the top of the object to the center of the lens. So from here straight up down here, and you know what, I'm gonna continue, goes down there. Okay, the light ray is going like that, and the intersection is over here, hence this is where my image should form. You can see, don't forget the label, you can see that it is upright, and upright gives us virtual, and it is less and it is diminished, so it matches our wood. It matches our wood that this is virtual, upright, and also diminished to compare with our object. Now, like I said, I want to erase this line. Okay, erase it, and I am going to draw the lens like this and like that. There. So I got my image, which is 10 centimeters, and I got my object distance, which is 20 centimeters, like that. So that's how you answer this question. Let's take a look at this question. Figure 7.3 shows a lens made from glass with a refractive index of 1.52. The radius of curvature of the lens are 10 centimeters and 15 centimeters. So we do not know which is this one 15, or maybe it's this one 15, or maybe this is 10, or maybe this is 10. So we are going to sketch so that we can see who is who, whose is which. So I have here one circle. We know that concave or convex lens both are made up of two spheres actually. Alright, now my lenses cannot be made up like this because this is a biconvex lens. What I can see here, because of my the lens that we have here, this is a convex meniscus, so it should be made of this side. Okay, but this doesn't show much, so I'm gonna put it like that. Now I got it. Now I got this side. Can you see that? This is pretty much the same as our the picture that was given in the question. So judging by these two circles, we have the green circle and the red circle. We can see that the green hat is much bigger than the red circle, right? So since we have 15 and 10 centimeters, so what do you think? Which one do you think is the 15 and which one is the 10? So obviously you can see that this one is the R1, which is the 15 centimeters, because it has, obviously it has bigger circle to compare with the red one. Hence the red one is the R2, which is 10 centimeters. That's how we determine which one has bigger R and which one has a smaller R. Now let's determine the focal length of this convex meniscus. Because we are given the refractive index of the lens, so it is best for us to use the lens maker's equation, which is 1 over f equals to n material divided by n medium minus 1 over R1 minus 1 over R2. This equation, this is what we call the lens maker's equation. So I'm going to do the substitution. You can see here I'm putting 1.52 over 1 because 1 is the air, and this is what is the refractive index of the glass, which is the lens, which is 1.52 minus 1. Now we want to determine whether the R1 is positive or negative, so as the R2. Alright, now let's imagine a light ray coming from this side. You can see that on the first surface that this is a Kuros, hence our R1 becomes negative. But what about the second surface? As the light ray continues to hit on the second surface, it is also a Kuros, hence our R2 is also negative. But madam, how do I know? Maybe I want to move it from the other side. So let's say I want to move from this side, madam. What's going to happen? So if you use this route where the R2 now becomes the R1, you will see that it is bone shape. It's okay. You're just going to put here positive 10 centimeters. And we're going to, as we continue on the second surface, which is now this one becomes R2, this will be also bone shape. Here we got bone shape. Then this one becomes positive 15 centimeters. We're going to see what's going to happen if you use any of these two. You're going to end up with the same. We're going to prove it in our video. Okay. So this one, we're going to use the yellow light rays first, which is negative 15 and negative 10. Okay. So we're going to add in here negative 15 minus 1 over negative 10. Your final answer for the F should be 57.69 centimeters. Okay, you got that one. So what happened if we use the orange route, which is this one from this side? Okay, if you use the orange route, you will have 1.52 over 1 minus 1 times 1 over 10 minus 1 over 15 like this, and you still gonna end up with the same answer. So no problem if you want to use the light ray from this side or from that side, you're still gonna end up with the same and correct focal length. The next question, if the lens is immersed in water solution of refractive index 1.35, calculate its new focal length. So what we're gonna do, we're gonna change this part. We're gonna change this part only, and we will see what happens. Okay, now we have 1 over f equals 1.52, but this time our the medium is becoming 1.35 instead of 1. So you minus 1, because originally it was in air, right? So air has a refractive index of 1, but this time we substitute into 1.35. The rest is the same. You know what? I'm going to just use the orange path, which is 1 over 10 minus 1 over 15. Okay? So you're going to end up with F equals to 26.64 centimeters. What does it mean? It means that when you immerse this lens in a denser medium than air, then your focal length of your lens now becomes shortened. So that's how it means. Now I want to discuss this question number 13. It says here, a thin plano-concave lens is made of glass of refractive index of 1.52 and has a radius of curvature of 30 centimeters. I won't be discussing until the end. I'm just going to discuss on why is it important for me to discuss this question, because they don't give us any picture. And because of that, we have to know the name of this plano-concave lens. How does it look like? But because we have discussed at the early stage of this video that a plano-concave lens should look like this. Okay, so what we have R1 and we have R2. For the R1, if the light ray is coming from this side, you can see that the surface is Kuros. Hence, your R1 is negative, and because it's given us the radius of curvature is 30 centimeters, I'm going to write here like that. Oops, this is too small. Okay. I'm going to put the R2 here, and you can see that for the R2 it is infinity because it's straight line. Okay, so from there I think that you can try to determine the focal length of the lens. I'm gonna cut it short. I don't have to explain it anymore, but I'm just gonna give you the answer. Okay, Okay, so if you have finished your calculation, you will see that f, we will get negative sign. So it means that this is legit a concave lens, because only concave lens can give us negative focal length. And if you look at the bottom one, which is we have to determine what is the image distance, you can see it is also negative, which indicates to us that this is VU, and obviously it's a D, diminished. So again, for a concave lens, you will always get VUD where the focal length is negative. That's all. Bye.